So let me introduce you to my PhD subject, which is the study of the mechanical consequences of femtosecond laser irradiation of metals. So I'm working at the École des Mines with the direction of András Barbetti and in Laboratoire Bercurien and with Jean-Philippe Colombier. So I will present to you the subject and then the physical principle of the metal pinning. And then I will detail to you how I'm doing numerical simulations and experiments, including laser irradiations and characterization. And then I will show you the results and perspectives of this work. So the goal is to understand the laser matter interaction during the pinning, the laser pinning. To do so, there are three main axes of work. First, the modeling of this interaction and with the numerical simulations. Second axis of work is experimental part with laser pinning and X-ray diffraction in order to characterize the microstructure evolution during the pinning. And third is to assess fatigue life with the irradiated samples. So in order to understand well this laser matter interaction, we are working on different material which have very different physical properties. So we have chosen aluminum, titanium, nickel, and iron. And we play with the laser parameters, which are fluence and pulse duration, to understand their impact. So I will now speak about the physical principle behind laser pinning. First, with the most well-known pinning, which is at nanosecond regime. The principle is to create and propagate a shock wave into the material. And during this propagation, if the shock wave shows high pressure, there is a local plastic deformation, and after the propagation of the shock wave, residual stresses are remaining, which will impact the mechanical properties of the metal, including its hardness, its fatigue resistance, or its resistance to corrosion too. So this technique is already well known and industrialized. One of its drawbacks is that there's a need for a sacrificial layer on the surface of the treated material in order to confine the shock wave and take it into the bulk. So here we are working on femtosecond regime laser pinning. The main difference is that there is no sacrificial layer needed on it, and that it produces a higher intensity shock wave, and that the thermal zone is reduced compared to nanosecond. The consequences are the creation of microstructural defects in the subsurface within the depth. The impacted depth is a few hundreds of microns, or few tenths of microns. So the physical origin of the shock wave in the femtosecond laser pinning is the disequilibrium which occurs between the electron's temperature and the lattice temperature. Why? Because at the femtosecond scale, only the electrons see the laser, and so the electronic temperature increases a lot, very fast, and during few picoseconds, there is a disequilibrium between the electronic and the lattice temperature, which leads to the creation of the shock wave and the propagation into the bulk. Then the equilibrium is made within few picoseconds. There is melting and ablation which occurs, and then resolidifications with microstructure modifications compared to the origin of the metal. So in order to model this this pinning, we need for sure to have a model which includes the motion of the atoms and the disequilibrium between the electronic and lattice temperature. For this, we chose to use the TTM-MD model, so which is coupling model between molecular dynamics, which is represented here by this second equation, and TTM, which is a two-temperature model, so which make the link between the electronic temperature and the lattice temperature, depending on the material and the electronic temperature, which is called the electron phonon coupling factor. To implement such a model, we're using LAMPS, which allows to do parallel calculations, and allows to set all the different parameters of the two temperature models, and to simulate the deposition of an energy of the laser. Then I will detail some of the methodology used for the experiments. So first, we are preparing samples of almost pure metals in order not to have particles in it or not to have too much parameter. So we are preparing it in order to have a very polished surface, a very plain surface, and no residual stresses, which we are checking thanks to XRD measurements. And then we irradiate those samples with very different fluence between, so these are the incident fluence, between 1 and 30 joule per centimeter square, and with various pulse duration also between hundreds of femtoseconds and 5 picoseconds in order to have a large range. So we are scanning the surface of the samples with such a procedure with the scanner, and then we are doing XRD measurements. So two different kinds of measurements: laboratory measurements, where we are measuring the diffraction peaks at various incident angles in order to calculate the residual stresses below the surface, and synchrotron measurements, where we are doing measurements below the irradiated surface at 1 micron step in order to have an accurate gradient of the dislocation density below the irradiated surface. So let me now present some results from simulations and experiments. So first, these are pressure maps obtained from TTM-MD simulations, where we can see, so here at the is the surface, and then we can see as a function of depth and times the evolution of the pressure wave. So here we have 4 different fluence from 2 joule per centimeter square to 12 joule per centimeter square. And we can see as a result of this that the pressure as a function of the incident fluence is almost linear. So this will lead to think that the created residual stresses below the surface will be a linear function of the incident fluence. And here are some results from synchrotron measurements. And so here is represented the strain energy stocked in the material as a function of the depth below the irradiated surface. So here for 3 different values, 2 to 10 and 20 joule per centimeter square, we can see the evolution, which is quite linear as a function of the fluence. And we can see that this stocked energy decreases in the depth of the material because of the decreasing of the shock wave, so which is relevant with the simulations. And we can see that the higher the fluence is, the higher the stock energy is. And here I added a 4th curve, which show a different regime, let's say, that at very high fluence. we can see that the behavior is not the same than for the other ones. There's a second zone here, which appears with lower values of torque energy. So this could come from a melting and recrystallization phenomenon, which occurs just below the surface, and which, in a way, erase the effect of the shock wave. This is currently under an investigation. So here are the perspectives for this work. As I just said, we'll investigate the near irradiated surface zone in order to understand how the melting and the recrystallization phenomenon impacts the laser pinning. And we'll do similar works on titanium, nickel, and iron, both on simulations and experimentals. And one of the next steps is also to do X-FEL measurements. So X-FEL is an electron laser in order to see the pressure shockwave formation and how it goes into the depth of the material in real time. So thanks for your attention.